Hey everyone, welcome to the Quimper Geological Society events. It's not very often that I get led in by the talking heads. Just a little music on theme to get us started. Thanks Marli and Michael for some of the suggestions there. If you think of any other songs as we're going that pop into your head that have to do with traveling or being on the road, feel free to pop those into the chat. My name is Rebecca Koranowski, and I will be your tech host for the evening. And we'll get started here in just a moment, but just a couple of housekeeping things. First off, we will have the audience with your mics muted for the duration of the presentation, just to prioritize the voices of the speakers that we have. But you are welcome to have your camera on or off, whatever your preference. We will be recording this session, but we won't be recording the audience's video feed. So if you're not speaking, you won't be a part of that recording. So feel free to turn on your camera and give us some audience so we know who's around. In Zoom, we have a couple of different ways that we can view the session. You may have seen the screen share slides that were just up a moment ago. And in the upper right-hand corner of your screen, if you're on a computer or if you are on a tablet or a phone, you can swipe left or right or click the view option to change how your settings, your viewing settings. When the screen share begins again, you may have some video feeds that are in the way of the slides, and you can just click on the black bar that's on top of the videos, on top of everyone's floating heads, and you can move those around or minimize them if they're getting in your way. We will be using the chat throughout the session, and feel free to pop questions into the chat as they come up for you, or hold them till the end. We will have a Q&A afterwards. And Michael and I will be posing those questions to Marli at the end of the session. If you have any technical questions, feel free to put those in there as well. I'm going to enable the closed captioning so that folks may turn that on or off. You may need to click the closed captioning button that is either at the bottom of your screen with two C's in a rectangle, or it may be behind the More menu. And if you'd prefer not to see the subtitles, you can click the up arrow and say hide subtitle if those show up for you, or you can click the up arrow and say show subtitle if you'd like to see them. And with that, I'm gonna load up our poll that we generally like to begin the session with. And Michael and Marli, just so you know, something may have popped up on your screen, and just leave that alone, and I'll push the buttons for us. It gets a little confusing sometimes when there's multiple hosts. Zoom doesn't know what to do. So yeah, we want to know who you are, where you're from, what your background is. And we added a third question today because of the awesome write-up that we had in the Port Townsend Leader. We're curious if folks have been sent to us from that article. And so any clarifications, feel free to put those in the chat. If the option isn't there that you'd like to choose, you can chat to us. And I'll leave this up just for another 10 seconds or so for us to collect some data. So there will be 3 questions. You'll have to answer each and then click submit. Ice Age Floods Institute. Thanks for coming, Larry. All right, I'm going to click end and share the results with you. If you miss submitting, feel free to send those in the chat. Okay, sharing the results. So Washingtonians outside of Jefferson County is our leading demographic location. Normally we have a lot of PT folks, so I think Marli, you're bringing in a wider audience for us today. Geologic background, we're at about 50% of folks with no geologic background, and then varying levels after that. And then a number of folks, 12 even here from the Port Townsend Leader article. So there you have it, Michael. And then people are also obviously reading your emails. So with that, I'm going to stop sharing. Michael and Marli, you might have to click the X at the top of that poll box there to get it out of your way. And with that, I'm going to pass it on over to Michael Machette, leader of the Quimper Geological Society, and take it away, Michael.
Okay, thanks, Rebecca, especially for that music you supplied us. Welcome to the Quimper Geological Society for this Zoom session. This is our second of 2022, and we'll have 2 more in the spring. It's being recorded, and it'll be posted on our website in a week or so. I'm pleased to say that our membership has stabilized around 1,000 members. I think that's pretty good for a little podunk geological society stuck up in the northwest corner of Washington. Yeah, I'd encourage you to look at our Facebook page and join that if you like. We don't post a lot, but Shelley J and I put things on there that are of interest to you or point you towards interesting geologic pages or events. So that's a Facebook page with the same name, Quimper Geological Society. Our next talk is on April 2nd, a Saturday, and features Kim Juniper, as in the bush, juniper, who is going to speak about seabed mining. Kim's the chief scientist of Ocean Networks Canada, and he's a professor at the University of Victoria in BC. Seabed mining is a futuristic and controversial international activity that's being driven by the search for exotic and valuable minerals. Okay, so that's what we got coming up. Say a few words about Marli here. I met Marli first in the late 1990s in Death Valley, where she was doing some mapping and I was doing some dirt work, but haven't seen her for a long time since then. She received her Bachelor's of Science in Geology from Colorado College. I was at Denver at the time. And she completed her Master's of Science and PhD in Structural Geology at the University of Washington here in Seattle in the early 80s. She's currently a tenured senior instructor and researcher in the Department of Earth Sciences at the University of Oregon in Eugene, where she maintains the website geologypics.com. Those were those photos you saw in the beginning, rotating through. 4,500 photo collection, probably more, Marli. Anyway, quite a resource if you're an instructor or an illustrator or just an author. This site has free downloads and their searchable geology catalog. In addition, she's a prolific writer. She's the author of Roadside Geology of Oregon, the 2nd edition, and also the Roadside Geology of Washington, the 2nd edition also, which she wrote with Daryl Cowan at UW. She recently created a book called Oregon Rocks, A Guide to 60 Amazing Geologic Sites. So those are the 3 things there. They're on Amazon or at your local bookstore. You might want to pick up, stuff it in your glove box, and hit the road. Okay, today Marli's speaking about geotouring the Northwest and encountering the unexpected. Without further ado, Marli Miller from Eugene. Thank you.
Hi, everybody. Thanks, Michael. I got to correct you, though. I got my PhD in the early 90s and not early 80s. Something I guess I'm sensitive about that. But thank you all for coming, especially on, it's a beautiful afternoon here in Eugene. And I guess it's pretty, I mean, I can see Michael's got clear skies behind him and palm trees, so it must be nice up there. I've always really enjoyed the times I've been in Port Townsend. I haven't been up there that much, but I was able to experience it a little bit when I was working on the Roadside Geology of Washington, and a couple times when I was at UW as a grad student. And I always really enjoyed it, but I never seem to have had enough time there. So I do hope I can make it back and actually spend some time. This talk comes out of writing those books, Roadside Geology of Oregon and Roadside Geology of Washington. It was it was amazing to be able to do that and to travel all over the states and see these amazing places and learn about the geology. But what would happen so often would be that I would see these things that I didn't really understand, and I would read about them, and it would just bring up more questions and things like that. So the title of this talk has to do with well, the point of this talk is to basically talk about the geology of the Pacific Northwest, to provide a context for some of these questions that would arise. And so without any further comments from me, I guess I'll start showing you some slides and talking about it. Let's see, I share the screen. Let's see. Okay. So, and everybody can hear me fine? Okay, thanks, Rebecca. All right, so I guess everybody here knows that we've got some wonderful landscapes in the Pacific Northwest. This photo is from Bandon Beach, and sort of along the coast, about halfway down Oregon. At low tide, you can go out and you can get a close look at these sea stacks. The Cascade Range, here's a view looking over the top of Mount St. Helens towards, here we go, Mount Rainier. And if you go into Oregon, you can see more of the Cascades. They go all the way down to Lassen Peak in Northern California. Over on the right are the Three Sisters. Here on the kind of towards the left is Mount Bachelor, and then on the far left is Broken Top Volcano. If you go up to the far northern part of Washington State, you get into the North Cascades, which Mount Baker, a volcano, is poking through the North Cascades, but most of the North Cascades are this, metamorphic and intrusive igneous rock that has been uplifted and exposed and is being deeply eroded by glaciers. If you go east of the Cascades, you get into much drier landscapes. This is looking down into the Yakima Valley. And in Oregon, in southern Oregon, you get into the Great Basin and Range Province, and you can see this is Lake Abert, and you can see as it's evaporating, it's leaving behind this crust of salt. So here's just a physiography of Oregon and Washington, and you can see it's really quite variable, and it's really it's great because it falls into these different provinces, if you will, that were very convenient for writing these roadside geology books, because each province would be a chapter in the book. So we'd have I'd have an introduction to the chapters, and then write about the roads, and then you could see there would be about 7 chapters for each of the books. But that's the physiography, and but as it turns out, the physiography and the geology are very closely connected. Here's a generalized cross-section across Washington State, starting in the west from the Juan de Fuca Plate, subducting underneath North America, and going all the way over here. This is the edge of North America as it was at the end of the Paleozoic era. And it's a pretty complicated cross-section, but what you really need to see is this heavy dashed red line here, which separates the basement rock from the overlying cover rock. And the basement rock has all been added on to North America since the end of the Paleozoic, which was ended about 250 million years ago. And actually the beginning of the accretion was younger than that. It was probably another 50 million years later. But these are all so-called accreted terranes, starting with Q here for Quinellia, and those are just abbreviations. And so in this talk, what I'm going to do is I'm going to start talking about some of the basement, and I'll talk a little bit about this accreted terrane called Siletzia, which is the most recently accreted terrane. and some of the things that it might tell us about the timing of uplift in the Olympic Mountains. I'll talk about the nature of the ancient margin of old Paleozoic North America, or the Laurentian margin. And then after that, we'll do like a little field trip up the Columbia Gorge, which is kind of nice because it includes both states, Oregon and Washington. And I'll talk a little bit about the boring volcanics, which aren't boring at all. Talk about the Yakima Fold Belt, and then mid-Miocene sedimentary rocks, which I think have a lot of really interesting things to say about Oregon and Washington. And I'll talk a little bit about the Missoula floods. So here's that cross-section. And you can see the cover sequence sitting on top of the accreted terranes. And here's a cross-section across Oregon, and you can see they're very similar. They both consist of accreted terranes on the edge of Paleozoic North America with a cover sequence. There's some differences. There's a lot of differences in the accreted terranes as well, but they both have Siletzia in common with them. And one of the hallmarks of Siletzia are these pillow basalts. They look like pillows. And these particular ones are from near the campground at Cape Disappointment, very southwestern corner of Washington, right where the Columbia goes out into the Pacific Ocean. And these pillow basalts, which you see throughout Siletzia, not everywhere that there's Siletzia, but just about most places, these formed in because Siletzia erupted underwater as a large marine, I want to say platform, a big submarine plateau, a gigantic submarine plateau. And there's actually sedimentary rocks interbedded with some of these that have marine fossils in them. And then you see these pillow basalts, which are typical of erupting under seawater. If you go down to Corvallis here, you can see there's a really neat quarry up on Mary's Peak, which is the highest point in the Oregon part of the Coast Range. You hear some cross sections of the pillow basalts. But what I really want you to see is the map on the right, because all that purple is Siletzia. It's the basement rock of the Coast Range. And in Washington State, it's called the Crescent Formation. I often call it Siletzia because the whole terrain is called Siletzia, but I'll kind of use the words interchangeably, calling it Crescent sometimes and Siletzia other times. But you can see that exposures of these basement rocks of Siletzia go from Roseburg all the way in the south. They go all the way up past Corvallis, up here to the northern tip of the Olympic Peninsula, and actually they go on to Vancouver Island. So it's this gigantic accreted terrain. If you go up to Olympic National Park, here's Port Angeles. You can take this Hurricane Ridge Road, and you can see the road goes right across Siletzia, right across this horseshoe shape of the purple. So that's the exposure of Siletzia. And here you can see these rocks are all those pillow basalts. There's lots of pullouts along the side of the road. You can pull off easily. You can get out and you can go pet the pillows. And you can see for sure that these really are pillow basalts. And there's actually some sedimentary rocks interbedded with these. And these have yielded marine fossils as well. But then you can keep driving and you get up to the top of Hurricane Ridge. And up here you can look across, you can see Mount Olympus. It's a fabulous view that I imagine a lot of you have been up to. And you can see once you get up onto Hurricane Ridge, you're in this Olympic subduction complex, which is shown over here on the left. And so Siletzia has been pushed up over this Olympic subduction complex, which is variably old, say from about 15 million to about 30 million years old. And it's really variable because the Olympic subduction complex came together in a subduction zone. It was stuff that was scraped off this descending plate and has been just kind of added on through time. So it's really variable and it's highly deformed. So if you were up there on up on Hurricane Ridge and looked at the bedrock exposures up there, you'd see that they're metamorphic rocks. They're kind of low-grade metamorphic rocks. They're but if you were then to drive down to the coast, you could see that there's sedimentary rocks, and these are actually younger. These are these nicely bedded sandstones and shales, and you can see that they've been tipped up on end. So you can see they've been deformed. You can actually see they're even more deformed than that if you look closely at the rocks, because these rocks have what are called graded beds in them, where they're coarser grained down here and they get finer and finer grained. And that's because the material, the sand and the silt and the shale was kind of came out of suspension. And so the coarsest grains settled first. So these are actually these rocks are completely overturned. If you go around the corner, you can see these rocks, which aren't just, these are highly deformed, these nice folds, and you can see they're actually detached from the rock underneath by a little fault zone. If you go to other places, this is Beach, you can see completely different rocks. They're all sedimentary though. These, if you look at them closely, these are sandstones, but they're really broken up. They're fragments. And here's this white thing is a piece of limestone that's in there. These are submarine debris flows. So it's really variable. And if you then go to Ruby Beach, which is located where the star is, you can see more of these debris flow deposits. I like to think everybody on the beach here is looking at the debris flow deposits, but that's probably not true. But you can go down there and you can take a look at these things. And one of the things we noticed, because when I was working on the Roadside Geology of Washington book, I co-wrote that book with Darrell Cowan at University of Washington, who was my master's and PhD advisor when I went to University of Washington. So we have this long-standing relationship, and we're become very good friends. And it was just wonderful to work on these projects with him, or this project with him. And we were down there and noticed how many of the clasts in the debris flows here were basaltic. And we think these are probably part of the Crescent Formation. And if that's true, it would actually be really pretty important, because if you look at the map and the cross section here at the bottom, you can see that the present distribution of the Crescent Formation is that it's on the other side of the mountains. So either it used to be on the west side of the mountains and it's all been eroded away, or the mountains have risen since these rocks were deposited about 15 million years ago. And they were deposited way out here where you'd expect debris flows to form, way out at the front of the accretionary wedge. So looking at the present distribution, they'd have a long way to go and have to get over the top of the mountains. But probably what's most significant about this is it corroborates this study by Brandon and others in 1998, where they argued that the Hurricane Ridge Fault, which brings the Crescent Formation over the top of the Olympic subduction complex, they argued that it actually carried it really pretty far to the west, and that it formed this kind of lid-like feature over the top of the subduction complex. And then the mountains, as they rose, they arched it upwards, and then more erosion took place, and then it left behind this horseshoe-shaped arcuate, outcrop pattern that we see today. So as far as the Olympic Mountains and Siletzia, I think they're kind of inextricably linked. We've got clasts of Siletzia, we think, in the Haut debris flows, which would suggests that the Olympic uplift took place after 15 million years ago, and that they also corroborate the idea that the Hurricane Ridge Fault carried the Siletzia terrane over the top of the Olympic subduction complex. Now here's a map showing accreted terranes on the west coast of North America. So gray is Paleozoic North America. The colors are the accreted terranes. And you can see Oregon and Washington here. You can see the Olympic subduction complex in yellow, and you can see Siletzia in purple. And you can see that Oregon doesn't have any Paleozoic basement in it at all, but it just clips the northeastern side of Washington right here. But it raises an important question. How do you know when you're on an accreted terrain? And most of the time you don't know because you're up in the cover. So you can't, these are the basement rocks that have been accreted. But there's different ways, but one surefire way to know that you're on Paleozoic North America is if you use the Grand Canyon as an example, which is located about where the star is. In the Grand Canyon, you can see this old basement rock that's is 1.7 billion years old. But on top of that, you have this sequence of sedimentary rocks. You've got sandstone, shale, and limestone that were deposited during the Cambrian period when the sea was moving up onto North America. And we see this same sequence of rocks all over the place in Western United States. We see it in Utah, we see it in Montana, we see it in Colorado and Wyoming. I taught for 3 years at University of Wisconsin, Eau Claire, and we had it in Eau Claire, Wisconsin. I mean, you see it pretty much everywhere where there was Paleozoic North America. But you don't see it on the accreted terranes because the accreted terranes weren't on North America then. But when you go to northeastern Washington, you can actually see this sequence. So here, this is in northeastern Washington. This is Sweet Creek Falls, which was one of my favorite spots actually, because usually when I was up there, it was stinky hot. And this is just a quarter-mile walk from the highway, and you could go, and it was nice and cool, and there was water. And there were these cobbles here that you can see, these kind of yellowish orange cobbles of Addy quartzite, which is the Cambrian sandstone up in northeastern Washington. And you can see these are just cobbles. So they've come down the stream from above. If you were to go up there, you'd find outcrops of this stuff, and it would be sitting underneath shale that was Cambrian in age, which is sitting underneath limestone, which is Cambrian in age. And then these rocks here is the Ledbetter slate, which is Ordovician in age, so just a little younger than the Cambrian. That's here, and that used to be a shale. So we've got that sequence of rocks here in northeastern Washington. And here's a geologic map of the region. That last picture was taken up here sort of near Medellin Falls, but all the gray is the Paleozoic rock. And so that must be North America. This dark blue is Quinellia, which is the first big accreted terrane. So it stands to reason that the margin of ancient North America and the accreted terranes is going to lie somewhere in between. Here's a cross section across the area from Kettle Falls right here to Tenasket, which is down here. You can see there's a lot of purple. These are highly deformed metamorphic rocks. These are so-called metamorphic core complexes that are much younger than the deformation and metamorphism was much younger than the accretion. But you can see over here by Kettle Falls that we've got Quinellia, and then the gray here is Paleozoic North America. So it stands to reason that the margin is right between them. But when you look at the rocks, and Daryl noticed this, we've got these highly deformed quartzites, we've got highly deformed amphibolites, and we've got calc-silicate rocks, all of which had a sedimentary protolith or started off as sedimentary rocks and were then later deformed. And Daryl said, oh geez, I wonder if these are actually part of the original Paleozoic North America. And if that's the case, then the actual margin would be farther to the west than we think it would be. It would be somewhere over here, preserved presumably in these metamorphic rocks. That's a question. We don't certainly have an answer to that, but maybe it's something that somebody wants to pursue. But either way, you know, you can start on, you know, here's Newport. You can get on Washington State 20, which has got to be one of the greatest roads in the world. And you can go west on this road. You know, you're on Paleozoic North America here all the way to Colville, and then you get into rocks of Quinellia, and you basically go across this cross section here. You see more Quinellia, you public graben through this area, more in all these intrusive rocks. Then there's the Okanagan Dome, another metamorphic core complex. Get back into Quinellia here at Tenasket, and you can keep going on Washington 20 from Twisp up through the Mettal region, and then you cross the Golden Horn Batholith and into the North Cascades. I mean, it's just an amazing road. And you know, all these accreted terrains that are highly deformed and metamorphosed in the North Cascades, and then you cross the Straight Creek Fault and you're into the Western Cascades Thrust Belt, and keep going, and yeah, I mean, it just keeps going. And then you end up on the Fidalgo Ophiolite here by Anacortes, keep following Washington 20, take the ferry across to Port Townsend, and then you're back on Siletzia. And so basically, Washington State 20 goes through North America across all these degraded terrains and back onto Siletzia. It just gives a great overview of the whole place. Okay, now let's go up the Columbia Gorge. Here's just a view looking out of a small plane, looking up the gorge. And these are two maps up here. So the Columbia River is not this wide. This is the map on the south is from the Roadside Geology of Oregon. The map on the north is from Roadside Geology of Washington. And I just stuck them together so you can see everything. But I want to make the point that it makes for a really great field trip to drive up Interstate 84 from Portland to the Dalles. You can cross over and go down Washington 14, or you can do it in the other direction. Either way, you can see all these features, and these are a lot of the high points you can see along the way. When I talk about it, I'll be kind of skipping back and forth, but mostly sort of working upriver. And so the main things I want to talk about here, going up the gorge, and there's a lot to see. So just kind of narrow it down to these, is that there's volcanism. You see a lot of mostly volcanic rock as you go up the gorge, and it dates back to the early Cascades. So the early beginning of the arc volcanism here. And you see the Cascade volcanoes, you see these boring volcanics, the Columbia River Basalt Group, and evidence of the earliest Cascades. There's the Yakima Fold Belt, which I'll talk about some. It's these rocks have been folded into these big anticlines and synclines, but this is one of the points of confusion I have. It's like, honestly, I'm not even sure what the Yakima Fold Belt is and when it formed. So I'll talk about that a little bit. The age of the Columbia River, I think most people don't have any problem that it dates back more than 12 million years, even longer. But I'll talk, it's a nice way to talk about the sedimentary rocks that really clinch that age and also can give us a better idea of what Oregon and Washington were like about that time. And then talk about the Ice Age floods a little bit. So here are two views. You can pick your road, which you prefer. I-84 is just crazy and intense, really great landscape though. You go underneath all those waterfalls and everything. Washington 14 is a lot mellower. It's a beautiful drive. But right off the bat, I just want to point out, you can see Mount Hood high Cascades, active volcanic activity. I mean, you know, Mount Hood has had a very active history. So high Cascades volcanic activity. But the thing I really want you to see here is Larch Mountain, which is a basaltic shield volcano. And it's part of these boring volcanics, which are not boring at all. They're named for the town of Boring, which is right here kind of in the center of the map, which is part of the whole Portland area. Boring does have a sister city in Scotland named Dull, which I always thought was kind of funny. And they have a bakery. Nice town. But it's got these great volcanic rocks that are named for it. And you can see they're pretty much all over the Portland area. They give Portland a lot of its shape. A lot of the topography in Portland is because of the boring volcanics. You can see all these buttes. They're typically cored by or made of boring volcanics. And they range in age. Actually, let me go back a slide if I can. They range in age here from actually 2.7 million years old to 57,000 years old up at Beacon Rock, at the far right side of that map, far east side. So they're really quite young, and they're really prolific. And so because of that, they're also considered to be a potential hazard. This is a major urban area, and you know, these things have been erupting on a geologic timescale pretty continuously for the last 2.5 million years. So it is something that people are concerned about. They're also, you know, they're also an enigma because they're off the axis of the Cascades. Here, these are represent the Cascade volcanoes. They form because the subducting Huanafuca plate comes down as it heats up, it dehydrates, and that causes melting up here in the continental lithosphere. But you can see the boring volcanic field is to the west, and so the plate really hasn't sunk deep enough to have all that dehydration take place yet. So there's various models which might explain how these have come about, but it's still, as I understand, it's still a bit of an enigma. Certainly not boring. And then here's Beacon Rock, which is the youngest part of the boring volcanics. It's 57,000 years old. You can actually hike to the top. It's got basically a trail that's really a staircase that goes all the way to the top. And there's something like 800 steps or something like that. And you can get some nice views of the Columbia River. There's a lot of trees up there though, so it's maybe not as good a view as you might hope. But it's this volcanic neck that was, it's only 57,000 years old, but it's just left standing there because it's been modified by the later Missoula floods that came down the gorge. In back of it, you can see those ridges, and those are made largely of older volcanic rocks. And if you go just a little bit up the gorge, you can see all the Columbia River basalt. I mean, Columbia River basalt is every rock, I think, that you can see in this photograph is Columbia River basalt. It's kind of everywhere. Here's a map showing its aerial distribution. It's related to the Yellowstone hotspot, which is another story in itself. The Columbia River basalt group, most of it erupted from southeastern Washington and northeastern Oregon and flowed all the way down to the ocean. It covers this huge area that's more than 200,000 square kilometers, and it's got a volume of more than 220,000 cubic kilometers. 94% of that was erupted by 14.5 million years ago. So between 17 and 14.5 million years ago, there was 206,000 cubic kilometers of lava that was erupted. Now, that's hard to get, I mean, hard to conceptualize, but basically the National Park Service in the Grand Canyon has estimated the volume of air in the Grand Canyon to be about a 50th of that. So it's about 50 times the volume of air in the Grand Canyon. Anyway, just an amazing province of lava flows that makes for a lot of great landscapes. And if you were to go just upriver a little bit from that last photo, you can see that those lava flows are not flat lying. They're actually at an angle here, and that's because they're folded. And they're folded as part of this Yakima fold belt that I mentioned before. So here's a physiographic map. Here's Yakima. The fold in the background that you can see, US 97 goes right over the top. That's Toppenish Ridge, which is labeled here as T. You can see the Columbia River down here at the bottom of the map. And you can see those ridges then, those are anticlines. Those are, you know, folds in the Columbia River basalt. And most people agree that these folds form because of compressional stresses that have been built up because of rotation of Western Oregon and Western Washington against a much more stable, say, backdrop, if you will, of Eastern Washington and Eastern Oregon. And so here you can see the Yakima Fold Belt in sort of the South Central Washington, YFTB. And I don't dispute that. I mean, it certainly makes a lot of sense that that's why these folds have formed. But really, I wonder, what is the Yakima Fold Belt? Here, it's really cut and dry. It's these folds. They're the Yakima Fold Belt. But if you look at a map of similarly aged folds across Oregon and Washington, you can see that they're not at all restricted to the Yakima area. They're everywhere, it seems. And so I wonder, what is the Yakima Fold Belt? I mean, up near Coulee City, you can see this monocline in the Columbia River basalt group. Is that part of the Yakima Fold Belt? I mean, it's roughly about the same age as a lot of them. Down near Clarkston, Washington, you can see this gigantic fold going pretty much east-west. It goes all the way to Lewiston, Idaho. Down in the John Day area, you've got the Picture Gorge, which is another big fold. And so it's the, you know, what actually is the Yakima Fold Belt creates a lot of questions in my mind. There's also a question in my mind about timing. Like, when did all these folds form? And can we suss that out? And to just kind of, you know, emphasize this, if we look at a couple of the folds in the sort of Yakima Fold Belt proper, we can look here in this area just north of Yakima. This is Mount Baldy on Umtainum Ridge. You can see this if you drive down the Yakima River Canyon. It's a big overturned anticline. Here, this down at the bottom, you can see an interpretation of the orientation of the lava flows, and you can kind of see that up here without the interpretation. And the studies that have been done on this by Stage and others in 2018, they've argued that this is an active fold. It's forming today. And what they see is that the thrust fault that cores this, and also at Manastash and Sela Butte anticlines, which are just right nearby, that they're all moving at 0.4 to 0.6 millimeters a year. And they found these are old normal faults that have been reactivated. But the point is they're active. And if you go down to the Columbia River to milepost 57, this is one of my favorite spots actually. You can see here, you can see tilted, this part of a fold on the limb of a fold, the Columbia River basalt group. And up here, you can see flat-lying 2 million year old Underwood basalt, which is part of the young Cascade volcanoes. So this fold must be at least older than 2 million years old. And if you look at these kind of in the whole context, you know, here's milepost 57 down here, and here's Mount Baldy up here. Milepost 57 is inactive, Mount Baldy is active. I don't really see much difference in their relationship to the rotation, except maybe being farther to the south west. I might think milepost 57 would be the active place. So there's a lot of questions about this, and it seems like it would be really nice if we learn more about when these folds are actually, the timing of these things. To continue with milepost 57, you can look right across the river from there. I make a big deal of milepost 57 because you can go onto Google Maps Street View and you can see all this geology from your computer. You don't even need to go there. You can even see the milepost and see it. I took this picture out of my car, which makes me kind of happy. But this is Mitchell Point. And Mitchell Point consists of Grand Ronde basalt, which is the lower part of the Columbia River basalt in this area. And then up at the top, Saddle Mountains basalt, Pomona member. So between 12 million years old and up here and down here as young as 15.6 million years old. So that's telling you that the rock in between those has to be in between 12 and 15.6 million years old. Up here, you can see there's a different texture to these rocks. These are conglomerates. These are gravels, part of the Troutdale Formation, which was deposited by the Columbia River. So it tells you that the Columbia River was here at least 12 million years ago. That's something I think most people know. I mean, you can look at lava flows in the Columbia River basalt, individual lava flows, and you can see some of them trace out shoestrings and things like that, and they look just like river channels, and they're even older than this. But here is sedimentary rock deposited by the river, very, concrete evidence that the river was here at least 12 million years ago. But perhaps more important, these rocks on the side are still part of the Columbia River basalt. They're part of the Wanapum basalt. And if you look at a close-up view, this is the edge of a canyon that's been carved into the Wanapum basalt. So all these river gravels were deposited against it. And so this is telling us there was probably a period of uplift that caused this erosion into a canyon where these gravels could be deposited. So there's all sorts of things at this place, Mitchell Point. Gravels there demonstrate the antiquity of the Columbia River, and they were deposited in a canyon, which suggests that there was uplift prior to 12 million years ago. And I'm wondering, could that be part of the Yakima Fold Belt? That uplift might be related. I don't know, but an interesting thought. Okay, well, that's the Troutdale Formation, Ellensburg Formation. All these rock units were deposited between the Grand Ronde basalt, lower part of the Columbia River basalt, and the overlying Wanapum basalt, all part of the Columbia River basalt group. Ellensburg Formation, you see this up near Ellensburg and surrounding areas. Vantage horizon, I took this picture along Washington State 14 west of the interstate, going out to the coast. The Maskell Formation is all over sort of central Oregon. This is near John Day. There's the Latah Formation near Spokane. There's others. But these were all deposited during the eruptions of the Columbia River basalt group. They've got different names and they're different rocks. So it seems like they could yield a lot of information about what was going on the surface of Oregon and Washington during this time. A lot of work was done in the 1980s and some in the 90s by Gary Smith, but really nothing has been done since to really pull all these together. But it's an important time. The Columbia River basalt group eruptions were between 16 and 12 million years. They went even younger. The early Yakima folds rhyolitic calderas in southeastern Oregon were erupting. There is arc volcanic activity in the Western Cascades, and the nascent Coast Range was uplifting. And I'm sure you could probably come up with some other things that were going on at that time. Okay, now here's a view looking up the Columbia River. You can see Beacon Rock in the distance. This is from Cape Horn. And you notice right away that the gorge is very asymmetric. It's got a very steep south side on the Oregon side and a pretty gentle kind of mellow side on the Washington side. And that's because the Washington side is prone to large landslides. In fact, this is all one landslide. It's called the Skamania landslide complex. This is the head wall along here. It goes all the way up almost to Beacon Rock. If you were to drive Washington 14 and you're down here, you go by some pretty big road cuts. Bedrock looks like, but actually that rock has been transported by the landslide. This rock out here in the river is part of the landslide complex. So these things are really big, and they take place preferentially on the Washington side because the rocks are inclined gently to the south, part of this Yakima fold belt. And so because they're inclined to the south, that promotes sliding towards the Columbia River. On the Oregon side, there's really nowhere for it to slide. You get some, you get rockfall and you get some landslides, but they're much smaller. You get big landslides though on the Washington side. And another thing that enhances that whole effect is that the Columbia River basalt here in brown is highly fractured, so water can seep through the fractures. It can seep through then this blue layer called the Eagle Creek Formation, which is also very permeable. And then it gets to the top of the Ohanapikosh Formation here, which has a very clayey, impermeable zone at the top of it. And that causes the water to pool, which buoys everything up a little bit, which then promotes the landsliding. So both the orientation of the rocks and the fact that there's this impermeable lower zone really causes a lot of landslides to take place in the gorge on the Washington side. Here's a view from up on Beacon Rock towards looking upriver. This is Eagle Creek Formation here, which is tilted very gently to the south. And here's this is what the Eagle Creek Formation looks like. These are mostly lahars from the Cascade volcanoes, but they're like 20, 22, 23 million years old. And you can see they're very permeable, like a lot of water can seep through these and get down to that underlying impermeable zone. And here's a view of the Bonneville landslide, which is part of the much larger Cascade landslide complex. But the Bonneville landslide here, which you can see goes out into the river, it caused the river channel to be deflected around it. This is Bonneville Dam down here, and this is the Bridge of the Gods right here. This landslide's only 600 years old, and it flowed actually it dammed the river, and it spawned this legend of the Bridge of the Gods, where you could walk across the river because the landslide went all the way across. And because it dammed the river, it backed the river up all the way to basically the Tri-Cities area, which made this giant lake, which then broke through the dam and flooded downstream. It would have flooded Portland to a depth of about 20 feet. So a massive flood about 600 years ago, which is really nothing in comparison to the Ice Age floods. At the end of the Ice Age, between about 15 and 18,000 years ago, a lot of floods originated from Missoula, glacial Lake Missoula, and flooded down the Columbia Gorge. The highest of these, the largest of these floods, crested more than 100 or nearly 100 feet above Vista House that you can see here. So you can imagine the scale of these floods. And look, there's Beacon Rock in the background. You can see how that would have definitely modified the shape of Beacon Rock. Just just unbelievable floods. You can't even imagine. If you're not familiar with the story of the Missoula floods, it really is pretty spectacular. During the waning stages of the Pleistocene, they were still advancing. These lobes were still coming down from the Cordilleran ice sheet into what is now northern United States. Here's the Puget Lobe, which certainly affected where Port Townsend is. But over here, you can see this lobe, it blocked the Clark Fork, which is a river that drains northwestern Montana. And in blocking the river, it caused this glacial lake Missoula to back up. It backed up all the way to Missoula, which if you look at the scale here, you can see is 100 miles away. And it continued, the lake, it went farther south of Missoula, down all the way down the Bitterroot Valley. But to really get an appreciation for the scale of this lake is in Missoula, you can look up on the hills and you can see these strand lines from Glacial Lake Missoula, which the highest ones are over 1,000 feet above the valley floor. So just an immense lake, which eventually broke through the ice dam. And then by breaking through the ice dam, these floods coursed down. Initially, they coursed down the Columbia. Later on, because this ice lobe advanced over the area, later on they were diverted down Moses Coulee and then Grand Coulee. There's a whole story there. But they would come down and they scoured out this whole area, creating the channeled scablands. It would empty the lake, and then the ice would advance over the lake again and block it up again. And this happened repeatedly over a period of about 3,000 years. Estimates are anywhere between about 40 and maybe up to about 100 of these great floods came down northeastern Washington and down into the Columbia. In a few places, there were some narrow spots in the channel, which caused it to back up. This one lake backed up almost all the way to Yakima here. Here at Kalama Gap, it caused the lake, a lake to back up all the way to Eugene. If you go up the gorge, you can see a lot of evidence for this. You can, see the very steep profile of Beacon Rock, but you can also see a lot of scablands. They're basically, if you just imagine these huge floods coming down, they're going to tear up all the topsoil. They're going to tear up a lot of the bedrock, and then they leave behind these scabs of bedrock that hasn't yet been torn up. So you get all these cool scablands. You just see a lot of them as you drive up the gorge. There's also deposits of the floods. There are some very coarse gravel deposits. There's some finer deposits where there were eddies, and in some of the lakes, there's even where there are temporary lakes, there were fine grained deposits, all sorts of different deposits. They're mined in Oregon for gravel, so they even now play an important role economically. So you can take all these different things in the Columbia Gorge, and you can put together like a little cross section here, showing these, the oldest rock at the bottom, and then you've got the Columbia River basalt in sort of brown. Here are the boring volcanics in maroon color, the high cascades in pink, even landslides up here, and there's Beacon Rock. But so there's all these different features. I think these are some of the most interesting, and volcanism dates back to the early Cascades, but we see a lot of other volcanic rocks and evidence of different volcanic events. There's the Yakima Fold Belt, which still confuses the heck out of me as far as what it really is, but it sure makes for some cool features in the gorge, including, I think, really influencing the shape of the gorge. Everything's dipping to the south because it's on the side of one of these folds. The age of the Columbia River, we have real concrete evidence for it being older than 12 million years. And there are all these sedimentary rocks throughout the whole region that are about the same age. And it seems like that could be a really interesting avenue of research. And then, of course, there's the Ice Age floods. And, you know, you can get some perspective on all this by comparing this cross-section of the gorge with the more regional one. And you can see that, yeah, the gorge is, you know, a much smaller place. And you know, there's no, right off the bat, you can see, well, the accreted terranes are all underneath the rock that's exposed in the gorge, but they're there. And the geology goes off in both directions for a long way, as do the stories that you learn and the questions that come up. And to really drive this home, here's Mount Rainier. And I mean, Mount Rainier was really a joy for me to learn about. But if you were to spend much time at all at Mount Rainier, you would see that, you know, you'd get to know it intimately. You'd get to know nooks and crannies and all this, and you'd learn that it has this history that goes back 500,000 years. And within that period of time, there are multiple eruptive periods. Some of these eruptive periods were pretty peaceful. They erupted effusive lavas. Others were much more violent, where you can see pyroclastic deposits. You can see that there's a whole story of interaction between the lavas from Mount Rainier and some of the glaciers. So there's a whole story there. But Mount Rainier is one of the Cascade volcanoes, one volcano of many, and yet it just makes up this little triangle here on the cross section. So it goes, there's so much more, and I think that's, for me, one of the greatest joys in working on these books was getting exposed to all these different stories, and the more I would learn, the richer those stories would become, and always there would be questions that come up, and then those create more stories, and it goes on and on. So thank you very much, and I'd love to answer some questions.
Thank you, Marli. That was perfect. You're right on 5 o'clock. We have a few questions in the chat room, but if you've got some rattling around your brain, throw them in the chat room and we'll serve them up to her as soon as we can.
Okay, should I, I'll go off of share screen, I guess.
Okay, Rebecca, how are we going to do this? You're off. There you are.
Yeah, thank you so much, Marli. That was wonderful. Yeah, a few questions here. First, from Tom, your map of the CRBG shows some isolated spots of CRBG on the Oregon coast south of the Columbia. How did it get there? So
oh boy, you just opened up a can of worms. Well, a lot of them just flow down the river, or basically where the river goes. And some of them, you can actually see Columbia River basalt as far south in Oregon as Seal Rock, which is south of Newport. And Newport itself, Yaquina Head, is Columbia River basalt. So yeah, there's a lot of Columbia River basalt on the coast. And the southern ones probably came across a channel that went across what is now the Coast Range, and nobody's been able to find it. But it would have predated uplift to the Coast Range. And then the ones farther north came down basically where the Columbia River is. And there's a whole story there, because a lot of the rocks of the Columbia River basalt form basically intrusions along the coast. There are these big, gigantic sills that have intruded parallel to the sedimentary layering. And it seems almost for certain that, well, these have been basically traced back up the river to subaerial lava flows. And the story there is that they actually were able to inject their way into the sedimentary material, mostly soft sediments, and work their way downwards and then reinflate as kind of magma chambers, some of which actually erupted. So there's on the coast, there's both lava flows that you would see on land and these intrusive material, these intrusive rocks, and it's all Columbia River basalt.
Okay, a couple more questions. I had one. The boring volcanics, are they in fact boring? What's the origin of that term?
What's the what?
Origin of the term boring volcanics.
Well, they come from the town, they're named for the town of Boring, where they're really well exposed. Boring, Oregon, so it's in the Portland area. I don't know how the name Boring, Oregon, how that town got its name Boring, but probably some guy named Smith. But the Boring Volcanics got the name because of the buttes around the Boring Hills around the town of Boring.
Okay. Carol Hassenberg asks, Marli, do the Washington Cascades have grabens formed in them the way the ones are formed in Oregon?
I guess I'm not entirely sure. There's so grabens like in the Basin and Range in the southern part of Oregon, in which case the answer would be no. But there's also the Oregon Cascade volcanoes. Sort of the Central Cascades have basically filled in a graben. That's just due east of Eugene and Salem. And I don't believe that the Cascade volcanoes of Washington have filled in, that those are related to graben. But there are older grabens, certainly like the Republic graben and the Chumstick graben, but those are all like 40, 50 million years old. And those might somehow relate to the accretion of Siletzia. But those would be much older. So I think as I read your question, probably the answer would be no, but there are graben that are to the, just to the east of the Cascade, the North Cascades of Washington.
Marli, could you just share to clarify what a graben is?
Thank you. Yeah, a graben is basically, here I'll draw a sketch. So if you, excuse me, if you have like two faults here, one like that and one sort of like that, and they're doing this kind of thing. And so the land between them would drop down, or the rocks between them would drop down like that. So that's a graben. And that forms by crustal extension. So you can see how this rock here matches this one, but it's been pulled apart that much. And we have, real graben in a couple places in Oregon. The Basin and Range part of Oregon are graben, and also then I mentioned that where like Mount Jefferson and some of the Cascade volcanoes fill in a graben. And Republic, the town of Republic is in the Republic graben, but that's older.
Rebecca, I've lost my screen. Can you feel the next question, please?
Sure. Yeah, thank you, Marli. That was super helpful. I love a quick diagram. Let's see, from George, we had a question. There are some large thrust faults and associated folds on the west side, like the Seattle fault, the Tacoma fault, the Olympia fault, etc. How are those related to the Yakima fold system?
I don't know. I've kind of always associated those faults, and somebody here might be able to chime in and give a better answer than I can. But I've tended to associate those with the plate margin. But there's a lot of faults that are inboard of the actual subduction zone that, in my mind, I've kind of attributed them to that. But I don't think those would be considered as part of this, Yakima fold belt. But on the other hand, when I was making that diagram showing the fold axes, any fold that would be happening now, I would have shown on that. So it's hard to separate these things out.
Yeah, and we just had Carrie also write in kind of on the same theme, and they were mentioning the Darrington Devil's Mountain fault zone as being potentially connected to that as well.
That's a much older fault, and that separates so if you go up to Burlington, basically north of there, you get into the Western Cascades thrust belt, which is probably about 100 million, between 100 and 80 million years old. And you go south of Burlington, you cross the fault, that fault that, and you get into these melange zones, which are also pretty old, but I think that fault is probably a much older fault. Michael, do you know the age of that fault zone?
I don't know right now. Sorry.
I think it's probably, kind of pre 50 million years old, which is when the Straight Creek Fault formed, because it really separates these different accreted terrains.
Okay. Rebecca, I'm still off screen. You
That's
can
okay. Just some comments. Folks did their research, or they already knew that the town of Boring is named after William Harrison Boring.
Okay.
Not a Smith, but not too far. And then we had another question. This one's from Michael. Your top 5 geologic roadside stops in Washington.
Oh my goodness. Well, the top one, it was pretty funny because Daryl and I were both talking about how, well, we should put our favorite stop and put it in the book. And he goes, okay, well, mine's Barney's Junction by Kettle Falls. And I'm like, well, that was mine. But then I felt compelled to come up with another one. But we ended up both saying it was Barney's Junction, where you can see these just terrifically deformed metamorphic rocks. So by Kettle Falls, that's definitely one of the spots. I really liked Cape Disappointment. I mean, you don't see a whole lot of variety of geology, but you see spectacular waves and beautiful pillow basalts. So that always stands out in my mind. Beach 4, which is where you can see those overturned sandstone and shale packages. That's another one that really stands out to me. Oh boy, there's 3. Certainly in the North Cascades, there's a couple places along Washington 20. And then I guess I really like, God, what's the number of the road? The one that goes up to Mount Baker ski area from Bellingham. That's a wonderful road. So there's places along there, Mount Shuckson. And I actually have a grad student who's working up on Mount Shuckson. And so I get to go up there a lot, which is pretty fun.
Okay. Do we have any other further questions? I don't see. Oh, here's one. Did we take care of this already? Are there large thrust faults and folds on the west side? Did you? Okay, I'm sorry. I was off.
That's it. Just a clarifying, Beach 4 is south of La Push.
Yes. So there's, it's funny, by La Push, there's, I guess, first beach, second beach, and third beach. And then you get on the main US 101, and there's Beach 1, Beach 2, Beach 3, and Beach 4, and Ruby Beach. So they've got just a different way of saying the numbers.
Mm-hmm. Yeah, those are near Claylock.
Yeah.
We did have one other question, and maybe we can make this the last one, and then if folks have more to check in with Marli on, maybe we can direct those to you via email. But someone was also asking your favorite 5 places in Oregon.
That's actually really difficult because I pretty recently finished this Oregon Rocks book, and everything that, you know, is just, there are just too many places. But I've gone taking my class to Devil's Punch Bowl, which is a beach just north of Newport. I'm taking them there next Saturday, and that really stands out in my mind as one of the greatest spots. Then there's so many amazing beaches. Hug Point State Park, just south of Cannon Beach, is another one of my favorites. I really liked Otter Point, which is south of Gold Beach, just north of Gold Beach. Again, those are all on the coast. And then there are these places in the Wallowas, and it just goes on and on.
Okay. Well, thanks. Wonderful presentation, Marli. We appreciate it very much, taking
Well,
your
thanks.
Saturday to join with us. And hopefully you can come to Port Townsend sometime and we can entertain you.
Well, I would love that.
It's the deal. Thanks very much. We'll see you guys in 6 weeks or so.
Nice meeting you all.
Thank you so much.
All right. Bye.